Doctor, I think you forgot to unmute yourself.
All right, Jiang. All right, I was talking alone. All right, okay. Good morning, everyone. So today we're going to continue what we have learned on. It was about the kinetic and static friction. Okay, so before that, we already discussed about the frictional force. Okay, so you learn what was the frictional force. Okay, so the friction is the one that is reverse to the force. All right, so it is okay. So if you look at the slide, so the friction is reverse to the push or pull force. Okay, so do you have any questions so far regarding what we have learned in the first week, second week, okay, and the third week? Do you have any questions? So remember that we're going to have our first test next week, okay, which will be covered until this topic, all right, this chapter 5. Okay, so if you don't have any questions, so let's continue with kinetic and static friction. All right, so we have learned about the frictional force. So now we have the kinetic and static friction. So friction have two parts, okay? So previously we only learned about what is the friction. So we can further divide the friction to kinetic and static. When it is kinetic, when it is static. Okay, kinetic friction acts when the object slides over a surface. So meaning that when the object is moving, so when your object is moving, so let's say I have this phone, so you slide it, right? So you slide it, so then that is when you have the kinetic friction. Okay, let's say I pull this phone, so you have kinetic friction acting on the body of the phone, all right, which is reverse to the direction of the pull force. Okay, and then the kinetic friction force is given by Fk equals to mu k n. All right, so we will discuss later what is the mu, what is n. So right now, just stay with Fk equals to mu k n. All right, the static friction acts when there is no relative motion between object. Okay, but when there is no motion, you call that as static friction. So the static friction force can vary between 0 and the maximum value. So the maximum value is mu s n. So Fs is for static friction. Okay, so it will be between 0 to the maximum of mu s n. All right, so the static friction is followed by the kinetic friction. Okay, so because we have the object first at the rest, so we have the static friction after, all right, okay, after that. So before the board slides, static friction acts, okay, but once it starts to slide, the kinetic friction acts. Okay, you look at the box there. So we have the box at rest. So there is no friction where Fs equals to 0. Okay, so when the board slides, the static friction acts, but once it starts to slide, okay, the kinetic friction acts. So like what I mentioned last week, so now Fs no longer is 0 because it is about to slide, but it hasn't slide yet. Okay, so let's say you are pulling, so now you are at rest, so Fs is 0. Now you have your hand on the phone and then you start to pull it. Okay, at the moment when you feel the force on your hand, but the object is still not moving. So that is when we have the static friction, okay, have some value. All right, it has some value. All right, the maximum value of Fs is just before object to slide. All right. Okay, so I hope you clear with when Fs is happening and then when Fk is happening. Okay. All right. So just before the board slides, the static friction acts, but once it starts to slide, the kinetic friction acts. Okay. Okay. The stronger applied force. So when we pull it stronger, of course, the object will about to move. All right. So the board's just about to slide. So the static friction we have Fs equals to mu Sn. Okay, so before the board slides, static friction acts, but once it's okay. So last one is when we have the object is already been slided. Okay, so now it moves. So we have now Fk. So Fk is equals to mu k n. All right. So let's see here. So we have the force. Okay, force. Okay, force applied until starting from 0 to a time t. So we look that we have a linear graph, okay, which is going to be from 0 to a maximum value where it is Fs at the maximum, where you have the mu s, okay, mu s n. All right, so Fs is at the maximum. All right, and then your frictional force, right? Your frictional force, when the object slides, you have it as Fk, right? So you know that Fk is a little bit smaller than Fs at maximum. Because of what? Because the object already slides, okay? And then at the same time, you have the frictional force. So when you, okay, you look at the phenomena over here. So when you pull it at the strongest point, so that is when you have the maximum frictional force available. Okay, because until that, you don't have to use much of your pull force to slide the object. So that's why you have the Fk is a little bit lower than Fs at the maximum value. Okay, so that is about the graph. Okay, so you look at the graph of Fk, so it will be a little bit noisy over there. So it's because the it will depend, all right, it will depend on the surface. So, but if the surface is more is rougher, right? Let's say it is on the ground. Of course, compared to, right? Let's say you are pulling a box on the ground, okay, compared to you pull it on the floor, okay, on the floor of the building, right? So of course the FK will be much noisier, all right, in the ground compared to on the floor. Okay, so this is the coefficient of the friction. Okay, so it is on different object. Okay, so when you pull a certain object on the object itself, okay, so you look there, so still on steel you have the mu s and mu k over there. All right, so the mu is the coefficient. Okay, so the mu is the coefficient. All right, so for the static friction, so we have the coefficient of mu s, and for the kinetic friction we have the coefficient of mu k. All right, so you look there, right? So we have the value of the coefficient. All right, so the highest from table, so we have 1.05, which is the copper on the cast iron. All right, and then that is the highest coefficient of static friction. All right, and then but interestingly, so we look there, the of the kinetic friction mu k is not one of the highest. All right, it is actually in the middle of the what we have among the others. Right, so we have it at 1.05, and then we have the mu k as 0.29. All right, so the lowest of the mu s and mu k is Teflon on Teflon and Teflon on steel, right? So why Teflon is having the most lowest static friction and kinetic friction is because, right? So you look at the composition of the object. So it is not heavy, all right? So the Teflon is not heavy, so that's why it has a small value of mu s and also mu k. All right, so you can just study this table. Okay, so we look at the phenomenon of static friction and the windshield wipers. So let's say we have the winter condition, so we have the squeak of the windshield wiper on a dry glass is a stick slip phenomenon. Right, so we have the rubber, so rubber acting on the glass. All right, so the moving wiper blade sticks to the glass momentarily, then slides, okay, when the force applied to the blade, okay, by the wiper motor overcomes the maximum force of the static friction. When the glass is wet from rain or windshield cleaning solution, the friction is reduced. Okay, so when it is dry, okay, when it is dry, let's say you pull the windshield wiper without the water, right? Without the water, you put on the screen. Of course, you will hear the screeching sound, right? So you will hear the screeching, like that, right? But when there is water, so when there is water, the sound is no longer there because it is lesser static friction. Okay, so static friction is less, and also the kinetic friction, okay, so the kinetic friction is higher compared to, sorry, kinetic friction is much lower at that time, okay, compared to the one before you put the water on the screen. Okay, so that's the phenomena of the static friction. All right, so let's say we have now, okay, so we learn about when we put the water. So let's say we considered about the fluid resistance and the terminal speed. Okay, so let's say if you have the fluid resistance acting on an object depends on the speed of the object. Okay, a falling object reaches its terminal speed when the resisting force equals the weight of the object. Okay, so let's say we have the diagram on your right. Okay, so we have the, okay, so we have an object that moves, okay, on the free fall, all right, on the free fall, but we have to consider the air drag. Okay, so we have to consider the air drag when it moves on the free fall. Okay, let's say the object, okay, right now on the left, so we have the dv squared. So dv squared now is less than mg, okay, meaning that the mg much bigger than dv at that time. So we have the speed of ay. Okay, right now it has the slower speed than the terminal speed where the object is accelerating and drag force less than the weight. Okay, at the terminal speed, okay, bt, okay, the object is in equilibrium where the drag force equals weight. Okay, so we have that concept right now. So before that, we don't consider the concept of the force when the object is in the free fall motion. Okay, now we consider that. So we have, okay, so when the object is moving further, so it's moving further down, so later it will have the drag force, which is the dv squared, it equals to the gravitational force. Okay, although we consider that as the weight, okay, which is equals to mg. Okay, so when at the terminal speed, we have the d squared equals to mg. Okay, so let's look at the graph. Okay, so when, okay, when there is no fluid resistance, the velocity keeps increasing. Okay, but when we have the fluid resistance, so we have the velocity at the maximum is vt, right? At the maximum as vt, which is the terminal speed. So that's the thing that we consider when we have the fluid resistance. We consider that we have the fluid resistance, then we have the maximum speed as vt. But when we don't consider the fluid resistance, then we don't have the vt. It's because the v will keep increasing. Okay, so now let's consider about the dynamics of the circular motion. Alright, so we consider already the movement on the vertical, alright, in the vertical direction, and also on the on the horizontal direction and the vertical direction as well. So the vertical, we consider that as the free fall. So For the horizontal one, we consider the movement of the object. So we have the frictional force. Okay. And then we consider now the circular motion. So if a particle is in uniform circular motion, both its acceleration and the net force on it are directed toward the center of the circle. So this is what we learned in the first few chapters ago. So we have the acceleration pointing towards the center of the circle, and then the net force on the particle. So let's see. So right now we have the net force of the particle is equals to F net equals to mv squared over r. Okay. All right. Now let's say we move. Right. So let's say we move we have the object moving. All right. So let's say over here we have example of a ball attached to a string wheels in a circle of a frictionless surface. So okay, there is no friction, so we don't consider any friction. So the ball of course will keep moving. If the string breaks, okay, so let's consider when we cut the string. Okay, so when we cut the string, then no net force acts on the ball. Okay, so because there is no longer F. Okay, as you can see from the picture, there is no longer F. Okay, so there is no longer F when the string broke. Okay, so the ball, okay, first it obeys the Newton's first law, okay, where it will be in the net force, okay, net force, so it's still moving on the circle, right? But when the string broke, then the ball will move in the straight line, okay, at the moment when the force is removed, okay, means that when the rope is cut. Okay, so let's see the example over here.
Here I have a circle with the segment of the circle removed, and I'll roll the ball in the circle like so. Now the question is, which can will the ball hit when it exits the circle? Will it roll around to hit the yellow can? Will it continue in a straight line to hit the white can? Or will it continue in a circular path to hit the green can?
Okay, so what's your answer to this? Anyone choose A? So the ball, okay, so it will hit the yellow can. Okay, the ball will hit the yellow can. So the yellow can, okay, at the bottom there. So we have the middle one, the white can. B and C, we have the green can. So which one is your answer? A, B, or this one should be simple. So who choose A? You can raise your hand. Okay, nobody choose A. How about B? All right. So majority of you choose B. Yeah, how about C? All right, nobody choose C. All right, so you already heard the clue, right? So it's on the straight line over there. So I also choose Okay, let's see.
Right, let's roll the ball to find out what happens. So as you can see, it hit the white can. While the ball was in the circle was keeping the ball in a circular path. Once the ball left the circle, there was nothing to act on the ball to keep it in a circular path, and the ball wanted to continue going in a straight line.
Okay, so you look that, so the last position of the ball, okay, so it will just move straight. Okay, so that's the answer. So right, great. So majority of you are correct. Okay, so for those maybe still not getting the concept, you can revise the topic again. Okay. Okay, let's continue. All right, so okay, so we also have the centrifugal force. All right, so let's say we have figure A shows the correct free body diagram for an object in uniform circular motion. Okay, so now the object is in the uniform circular motion, and figure B shows a common error, right? And then it says that an initial frame of the reference, there is no such thing as the centrifugal force. Okay, let's say you look at the A, so we have, okay, you mean that the force, both of the force going up and also the A also going up. Okay, if you include the acceleration, draw it to one side of the body to show that it is not a force. Okay, so it is wrong for you to label that. Okay, so to label that the quantity mv over r, okay, going down, because whenever you draw that on the horizontal or the vertical object movement, so you have the reverse force, right? So you have on the left side and also the right side. Okay, so before this you have, okay, the force acting there and also over there. Okay, and when it's going up, it's also going down. So when we have the object in the vertical motion, so you have there and also there. All right, but in the circular motion, all right, so this is not a force. Okay, A is not a force, so you only have, right, F towards the center, right? So this F is actually part of the acceleration. Okay, so here we have that the quantity, so we have that before we explain that the A equals to mv squared over r, right? So but that's not a force, so this one is not a force, and then it doesn't belong in the free body diagram. Okay, so what force that we have? Another one. Okay, so you look back, so we have the velocity, but this is not a force. All right, so remember that it is not a force. So we have only force acting on the moving object in the circular motion towards the center of the towards the center of the circle. All right, let's see. We have a car. Okay, so this is in the circular motion. Right, so we have a car rounds a bend curve. At what angle should a curve be bent? Okay, so a car can make the turn even with no friction. Okay, so let's say we have example here. Okay, we have a car rounding a bend curve, right? So it is in the, okay, so we have that car at that angle. Okay, at that angle, so it is actually like a velodrome, right? It's like a bicycle velodrome. So the track, so actually it's a little bit curved. Okay, so if you know about the NASCAR racing, so we have that kind of car velodrome. Okay, so the normal, okay, so we have the radius R over there, and then we have the car making an angle. All right, so making an angle, so let's say this is the track. Okay, so that track, and then we have the car at making the angle. Okay, making the angle from the horizontal, so we have beta, and then also for the vertical we also have the angle to that direction, so we have that angle and also angle over there. So of course it will be equivalent. So when we have, because the car is like a square, all right, so we consider it a square. So when we have that angle, so of course it will still be 90 degree to that. So when we have beta over there, and we also have beta from the vertical, all right. So okay, it said normal to the road is at the same angle from the vertical as the road is from the horizontal. So we look for the free body diagram of the car. So where we have, okay, so we have the weight acting, all right, so the weight of the car, W equals to mg, all right, and we have the force, the normal force, okay, on the top. Okay, so because it is should be the normal to the roof of the car. All right, so we have n, so we need to have the component of n in the x and y. So we have that n cos beta to the y-axis and n sine beta, right, to the x-axis. Okay, and then as usual, because it's circular motion, so we have the acceleration towards the center of the circle. Okay, so that is the free body diagram, okay, for the car. All right, so the fundamental forces of nature. So we have, according to the current understanding, all forces are expression of four distinct fundamental force. So this is summary of what we learned, right? So we have the gravitational interactions, okay, the electromagnetic interactions, okay, the strong interaction and the weak interaction. Physicists have taken steps to unify all interactions into a theory of everything. Okay, so that is a theory of everything. All right, any questions so far? We will continue with the chapter 6 after this. So,
Okay, okay.
okay, no question. All right, we will continue with chapter 6. All right. Okay, so chapter 6 discuss about the work and kinetic energy. All right, so what will you learn? So it's about the force to do a work on an object and how to calculate the amount of work done. All right, so before that, in the chapter 5, you learn mostly about the free body diagram. Okay, and now we will learn about how to calculate the work. All right, the definition of the kinetic energy, right, and the relationship between the total and change of the kinetic energy. All right, and also something about power. Okay, power is the rate of doing work. Okay, for example, okay, we have a baseball pitcher. Okay, does work with his throwing arm to give the ball a property called the kinetic energy. Right, in this chapter, the introduction of the concept of work energy and the conservation of energy will allow us to deal with problems in which Newton's law alone aren't enough. Okay, so before this, we learn about the Newton's law. Okay, so there is also a concept of the conservation of energy. So mean that the motion's law is only about the motion, right? We don't consider the energy involved with the object. Okay, now we're going to consider that. All right. Okay, so what is a work? Okay, a force on an object does work, okay, if the object undergoes a displacement. All right, so displacement when the box, if you look at the picture there, so these people are doing the work, okay, to displace the car. So let's the car move, right? So we can consider the work from the people trying to move the car. Alright, so if a particle moves through a displacement S, so you look at the box there, okay, while a constant force F acts on it in the same direction. Okay, so the work done by the force on the particle is W equals to Fs. Okay, so that's the work. So we can consider that S is a vector of displacement. Alright, so in which direction and how much it has moved. Okay, so that's F, right? And we also have F is the constant force. So the unit for work is Joule, right? So from the name of James Prescott Joule, okay, so he was an English physicist in the 19th century. So because of W equals to Fs, the unit of work is the unit of force multiplied by the unit of distance. Alright, so we have 1 joule equals to 1 Newton. So Newton from, it is from F, right? And S is because the displacement is m, meter. Alright, so 1 joule equals to 1 Newton meter. If you lift an object with a weight of 1 Newton, a distance of 1 meter at a constant speed, you do 1 joule of work on it. Okay? So work done by a constant force. Right, so the work done by a constant force acting at an angle to the displacement is, so this is where we consider that a certain angle, all right? So let's say we have an object, okay? So sorry, we have an force to lift up to a certain angle. So you have the object here. So let's say over there. So let's say you try to that direction. So you have the force over there. So that's W equals to Fs cos phi, right? It's cos phi. So phi is considered the angle between F and S. So if the object move like that and you have the force there, so that's the angle over there. Okay, so that can be considered as W equals to F dot S. Okay, so that's the vector. So look over here. So this is what is meant by the phi. So you have the force, okay, and then you have the S, and then the phi is between F and S. Okay. So when the force has a component in the direction of the displacement, the work is positive. Okay, so when we have the negative work, so we have the negative work when the force has a component opposite to the direction of the displacement. So the work is negative. Okay, so the work is negative. So you still look at the angle there. So we have the angle of phi. It's actually from S to F. So now the phi is more than 90 degree. Okay, it's more than 90 degree. Okay, so let's say we have the force which is perpendicular to the S. Okay, then there is no work. Okay, so there is no work. Okay, for example, over here, we have a weightlifter. Okay, it does no work. All right. So you see that the weightlifter is pushing. All right, is pushing up. Is pushing up the weight. All right. But it does not do any work. Okay, on the barbell. All right, as long as it holds it stationary. Okay. So if it holds that the barbell stationary, okay. So because the force, all right, the force on the barbell, of course, going down, all right, and then the weightlifter have the force pulling up. Okay. So that's why. So at the moment of the stationary, we have the displacement of 0. So that with that weightlifter does not do any work. Okay, let's say now the weightlifter lowers the barbell to the floor. Okay. Okay, the barbell does positive work on the weightlifter hands. Okay. So this is the barbell does the positive work on the weightlifter's hand, and then the force of the barbell on the weightlifter's hand is in the same direction as the hand's displacement. Okay. So that's the force of barbell on the hand. Okay. So the S is going down. Okay. S is going down. So F, the force from the hand also going down. So it will be the same direction of both F and S. Okay. So when he does the negative work, so he does the negative work when he's pulling out the barbell. So where the F, okay, where the F is in the reverse direction of the S. Okay. So that's the difference. The force of the weightlifter's hand on the barbell is opposite to the barbell's displacement. Okay. All right. So let's define what is the total work. So the work done by the net force on a particle as it moves is called the total work. Okay, if the particle speeds up, if W total bigger than 0, right? So the particle will speed up. Okay. for example, you see the box there. So if it moves to the right direction, so if it speeds up, so we have the W total bigger than 0. It slows down, okay, if W total is negative or less than 0. Okay, and if it maintains the same speed, okay, if W total equals to 0. Okay, so let's look at example.
Example 6.2, a tractor pulls a sled loaded with firewood a distance of 20 meters along level ground as shown in this diagram. If we look at the forces acting on the sled, there's a weight acting down, there's a normal force acting up, there's the force the chain's applying to the sled, called F sub T for tension, and of course there's a frictional force pulling back the other way. So we're going to calculate the work done by each of these forces. To do that, we'll need a coordinate system, and we'll take the x direction as the direction of motion of the tractor as such. Given these forces, we can now draw out the free body diagram. And here's the normal force, the weight, the frictional force to the left, and the tension force of the chain. We're given the magnitude of the tension force, the magnitude of the frictional force, and the weight. And we're told that the displacement is 20 meters, and of course that's going to be along the positive x-axis. The angle that the tension makes with the positive x-axis is 36.9 degrees. We'll calculate the work done by considering the magnitude of the force applied times the magnitude of the displacement of the tractor times the cosine of the angle between those two vectors. And we notice just by inspection that the work done by the weight and the work done by the normal force has to be 0 because the tractor never moves in the y direction. These two forces are always at a right angle to the motion of the tractor. The tension force, however, will give rise to work. So here's the size of the tension force, here's the magnitude of displacement and the angle between them, and the cosine of 36.9 is 0.8, and putting in the numbers, I get 80 kilojoules of work. And that work is positive because the sled is moving in the direction that the chain is pulling. Now let's look at the work done by friction. Again, the magnitude of the frictional force, the displacement. Now the cosine of the angle, or the angle between the two vectors, is 180. The tractor is moving to the right, friction is pulling to the left. And whenever a force pulls in the opposite direction the object is moving, that force will give rise to negative work. And indeed, I pick up a -1 from the cosine of 180, and I get -70 kilojoules of work. The total work can be attained in approach 1 by simply adding the work done by each of these forces, as shown here, and I get 10 kilojoules. A second approach is to actually calculate the net work done, the net force in each direction. So the net force in the x direction is obtained from the components of each force in that direction. So I'm going to have an ft cosine phi for the x component of the tension force. Here's the friction force to the left. Put in the numbers and I get 500 newtons. The net force in the y direction, of course, has to be 0 because there's no motion in the y direction, and there's no acceleration, so they have to sum to 0. So the total work will be equal to the scalar product of the net force into the displacement vector. The displacement vector only has an x component because the tractor only moves in the x direction. So all I need is the x component of the net force, which I calculated to be 500 newtons. And again, I get 10 kilojoules. Both methods give me the same number. And I note that, in fact, the total work done is not 0, it's positive. And when positive work is done on a system, that system gains energy from the work. In this case, the energy is going to be in the form of kinetic energy. So in fact, the sled accelerates. And this ends example 6.2.
Okay. Alright, such an interesting example. So we have a farmer try to pull a crate, okay, of object using his tractor, okay. So he pulls it a distance of 20 meter along a level ground. The total weight of sled and load is 14700. Okay, so that's equals to W equals to mg. Right, and then the tractor exerts a constant 5,000 Newton, okay, force at an angle of 36.9. So of the force from the tractor at an angle 36.9. Okay, so you draw that in terms of free body diagram. So you can see that we have now we have 3,500 Newton friction force. So friction force going to the left. Okay, so what we need to do is to find the work done by each force acting on the sled. Okay, and the total work done by all the forces. So what we have,
Example called application of the track. The angle that the
okay,
tension
so
makes
first we draw the free body diagram. Okay, so we draw the free body diagram. So we have the normal force, the weight force, okay, the friction, and also the force due to the tractor. Okay, the pull force at angle 36.9, and also we have S equals to 20 meter. Okay, so find the work done by each force acting on the sled. Okay, so W, so work, okay, work on W, okay,
displacement of the tractor
equals
times
to
the cosine of the normal force has to be zero because
work
the
on
tractor
normal,
never moves in
it
the
will
y
be
direction.
0. Okay, of course it will be 0 because we have that object. Okay, we have that object move to the horizontal. Okay, so that's why we have S is mentioned as 20 meters, so we don't have any work on the vertical axis. So that's why W equals to Wn equals to 0. Okay, and then the next one, so we need to have the component on the x direction. Okay, so we have the work from the track, okay, minus
Cosine of 180, direction the object is moving, that force will give rise to negative work, and indeed I pick up a -1 from the cosine
okay,
of 180.
so we have the work from the tractor. All right, so that's
The
80.
total work can be
All right,
attained.
and then we need to minus with the work from the friction. Okay, so the work from the tractor is Ft 36.9. Okay, so we obtain that as 80 kilojoule, and then Wf Fs cos 180. Right. Why 180? Because you consider that the object is already S. The displacement S is on that direction, but this F, the friction force, to the left direction. So we need to consider to the angle. Okay, so the angle between S and F, then that's why we take 180. All right, so 180 is -1, cos 180 is -1, S 20 meter, and F force is 3,500. All right, so you obtain that as -70 kilojoule. Okay, so you have two ways to calculate the W total. So you know that on the right direction is 80, just minus with 70. So you sum up, okay, you sum up all the force, so you get 10 kilojoule. Right, for the second approach, okay, you consider what is the total force first. Okay, so you consider what is the total force, and then later you will multiply with S. Okay, you will multiply with S to get your W total. Right? So it doesn't matter which way, but the first one is already, because you already calculate all of that. Okay, so that's why it is easier to do the approach number 1. Okay, so that's example on the total work. Okay, let's continue. Alright, now we move to the kinetic energy. So the energy of motion of a particle is called the kinetic energy. So K, kinetic energy, is equals to half mv squared. So I think you are familiar with this. Okay, like work, the kinetic energy of a particle is a scalar quantity. Okay, and it depends on the particle's mass and speed. Okay, not its direction of motion. Okay, the kinetic energy can never be negative, and it is zero only when the particle is at rest. Okay, so kinetic is the movement energy, so it cannot be a less than zero. So it can be zero when it is at rest. Okay, and the SI unit of the kinetic energy is joule. So you remember that the energy unit is joule. Okay, energy unit is joule. And also the work unit is also joule. Okay. The kinetic energy does not depend on the direction of motion. Okay. So let's say we have there the same mass of the two boxes. They are the same speed, different direction. So the motion have the same kinetic energy. Okay, the kinetic energy increases linearly with the mass of the object. Okay. So let's say we have the two boxes there. So we have one with mass of m and another one with mass of 2m. Okay. So the twice the mass, the same speed. Okay, but the twice the kinetic energy. So the speed is same, but the kinetic energy is double because the kinetic energy depends on the mass, half mv squared. So your m now is double, so of course your kinetic energy is double. Okay, the kinetic energy increases square of the speed of the object. Okay. So we have the, let's say now, we have half mv squared. So when v is double, of course the kinetic energy is also b is not double right now, so it will be 4 times higher because the v is squared. Okay, whenever you double, it will be squared. All right, so same mass, twice the speed and 4 times the kinetic energy. All right, so let's look at the theorem. So we have the work energy theorem. Okay, the work done by the net force on a particle equals the change in the particle's kinetic speed, kinetic energy. Okay, the work energy theorem. So we have the work done by the net force on a particle equals the change in the particle's kinetic energy. Okay, for example, we have the W total equals to the final kinetic energy, which is K2 minus K1. Okay, the initial kinetic energy, and then the delta K is the change in the kinetic energy. Okay. All right. So let's say we have the work and kinetic energy in a composite system. So the work done by the external force acting on the scatter is 0. For example, we have the scatter there. But the kinetic energy changes nonetheless. Alright. Why? Because this is explanation that is not adequate to represent the buoy as a single point mass. Okay, let's see the tutorial video.
In conceptual example 6.5, two ice boats hold a race on a frictionless horizontal lake as shown in this diagram. The boats have identical sails and feel an identical force due to the winds, shown as F in the diagram. However, the blue boat has twice the mass as the red boat. Now, if the boats start at rest and race over a distance S, the question is which ice boat crosses the finish line with a greater kinetic energy? So both ice boats travel the same distance S, and they feel the same force due to the wind. So the work done by this force is the same for each ice boat. It will simply be the force times the distance, since the boats are moving in the direction the force is pointing. By the work energy theorem, this work must be equal to the final kinetic energies, which is what we're interested in, minus the initial kinetic energy, which is 0 since they start at rest. And we discover that each ice boat has the same kinetic energy. However, they will not have the same velocity. The lighter boat will have a velocity that's square root of 2 times larger than the heavier boat. And this ends example 6.5.
Okay. From this example, so it is about
Conceptual example.
Okay. Alright. So it is about the what we call that. Alright. So which ice boat crosses the finish line with the greater kinetic energy? Okay. So when you look at the example there, so the blue boat have the 2 times of the masses from the boat, the red boat. Okay. So, but you look there, so this boat, okay, travel at the same distance F, okay, and then they have the constant force F along the direction of the motion. Okay, where we consider the work done is equals to F times F. Okay, so the boat have the same F because the wind exerts on the same constant force F on each of the ice boat, right? So when the total work is similar, the
Direction the force is pointing.
total work will be K minus 0. So the boat actually has the same kinetic energy. Alright.
Energy.
Okay,
However,
it has the same kinetic energy,
velocity.
but
The
it
lighter
will not
boat
have
will
the same
velocity that's square root of
velocity. Because of what? Because it is heavier. Alright, of course the kinetic energy will be slower. Sorry, the velocity will be slower on the blue boat, okay, compared to the boat on the red. Okay, so meaning that over here we have, okay, let's say the kinetic energy half equals to mv squared, right? And then the kinetic energy for the boat should also be half mv squared, right? So what is the kinetic energy? Sorry, what is the velocity of the blue boat? Okay, so you need to solve that. So let's write it somewhere over here. Okay, so let's write somewhere over here. So this is the energy for the red bolt. So this is for the red bolt. And then this also the kinetic energy for the blue bolt. Okay, let's say this is M1 and then B1, M2, V2. Okay, this is blue. Okay, because it is similar, so half can be crossed. M is M, and V is V. We need to know what is our V2. So we have here we have 2M. Okay, and then V2 2. So we have V2 equals to, right, half of 1/2V squared. Okay, so this is the speed of the blue bolt. Alright, so that's the speed of the blue bolt. Okay, so it has the slowest speed compared to the red bolt. Okay, let's say, okay, now we consider that we will work an energy with varying forces. So many forces are not constant. Suppose a particle moves along the x-axis from x1 to x. Okay, a particle moves from x1 to x2 in response to a changing force in the x direction. Okay, so let's say over there, so we have the object moves from point 1 to x1 to x2. Okay, so the force Fx varies with the position Fx. Okay, so let's say you have the Fx, F1x at the x1 to the F2x to the x2. Okay, so the distance, the difference in the distance will be x2 minus x1. Okay, and then you look there. So we have the graph of force as the functional, the function of the position. Okay, so we calculate approximately the work done by the force on many segments on the path. So because it is not linear, alright, because it's not linear, so we need to consider multiple bar. Alright, so we take a small bar so we can consider the work. Okay, so consider that the bar into segments. So we do this for each segment and then add the results for all segments. Okay, let's say over there we have segment of XA, XB until XF. Okay, so the work done by the force in the total displacement from x1 to x2 is the integral of Fx from x1 to x2. Okay, on a graph of force as a function of position, the total work done by the force is represented by the area under the curve by the initial and the final position. Okay, so we consider that area under the curve, I think from the first position to the final position. Okay, let's say the work done by a constant force. So that W now still area under the graph, but it is easier because it is a rectangle. Okay, so it is rectangle area under the graph represent the work done by the constant force of magnitude F during the displacement F. Okay, let's say we stretch a string. So the force required to stretch a string, a spring, a distance x is proportional to x. So where fx equals to ax. Okay, so the area under the graph represents the work done on the spring to stretch it to a distance. Okay, x, where the w equals to half kx squared. Okay, so why half? Because it is linear. Alright, so when it is linear, of course it will be half of the previously we have square. We have rectangle. So now you look there, it is sliced. It is sliced half of the rectangle. So that's why you have w equals to half kx squared. Okay. So the work energy theorem for motion along a curve. So we have a particle moves along a curved path from point P1 to point 2 acted on by a force that varies in the magnitude and direction. Okay, so the work can be found using a line integral. Okay, so before that we have the integral to find the area under the graph, which is similar to the total work. All right, now when it moves in the curve, or let's say a circular motion, so we consider the angle, all right, and also the to the line integral. All right, line integral, where so you have the curve, so you need to consider the line integral over there, which is you make a tangential line. Okay, where you make a tangential line. Okay, so during an infinitesimal displacement, so let's say it's a very small displacement, dl, the force does work dw on the particle. And then dw, okay, because dw is work, okay, so equals to f dot dl. Okay, and then f cos phi dl. So it's how to solve it. Okay, so over down there we have w. Okay, so it's between 0.2 to 0.1. So we want to find the integral f dot dl. Okay, and then because f that we have angle of phi, so s cos phi dl. Okay, and then we have, all right, so a component of f parallel to dl, so we consider that, so it is equal to that. So let's look at the example.
Motion on a curved path. At a family picnic, you are appointed to push your obnoxious cousin, Throckmorton, in a swing. His weight is W, the length of the chains is R, and you push Throcky until the chains make an angle theta naught with the vertical. To do this, you exert a varying horizontal force F that starts at 0 and gradually increases just enough that Throcky and the swing move very slowly and remain nearly in equilibrium throughout the process. For part A, we want to find the work done on Throcky by all the forces. For part B, we want to find the work done by the tension in the chains. And finally, for part C, we want to figure out the work required to push Throcky. And luckily, we can ignore the weight of the chains in the scene. So for the identify and setup portion, we're going to look at a picture of Throcky, and then we're going to look at his free body diagram. So the picture shows Throcky at some arbitrary point along his path. So at this moment, he's swept out an angle theta. So what we know is that theta is some variable, and it's some angle between 0 and theta naught, because we're starting at 0, he was down here at theta equals 0, and he ends up at some angle theta naught, because that's what they told us in the problem. So the reason we can just pick an arbitrary point is that we were told that he was in equilibrium during his whole path. And what that means is all of his forces along the whole path will be adding up to 0. So then looking at his free body diagram, corresponding with this picture, so that allows us to have this theta be the same as this theta, we can see all the forces. We have the force applied by the pusher going to the right, we have his weight down, and then we have the tension in the chain going up and to the left. And it's also broken into its components, t cosine theta up and then t sine theta to the left. So now for part A, we wanted to find the total work done by all of the forces on Thraki. So to answer this, I'll read a portion from the problem. We have that Thraki and the swing move very slowly and remain very nearly in equilibrium throughout the process. So this whole time, again, all the forces add up to 0. So if the sum of the forces in the x direction are 0 for this whole path, some of the forces in the y direction are 0 for this whole path, there should be no work done. And then for part B, we want to figure out the work done by the tension in the chain. But as we can see, the whole time, the tension is perpendicular to motion. What we should know is that work is a function of a dot product. And instead of writing f dot dx, we can write f cosine theta dx, where theta is the angle between the force vector and the dx vector. So that tells us that if we have two vectors that are perpendicular, that is, the angle between them is 90 degrees, you plug that into the integral, cosine of 90 is 0. So the work done by a force perpendicular to the motion is going to be 0. So that means the work done by the chain is 0. So now for part C, it's going to get more interesting. We want to figure out the work done by the applied force, the force made by the pusher. So as we can see, as Thraki moves along this path, the applied force, which is always to the right, starts to create a bigger and bigger angle between it and dl. So we're going to have to account for that. And what we can do is use an integral, and specifically use the one I just wrote, this one. So what we have is the work is equal to the integral from point 1 to point 2 of f times the cosine of phi times dl. So the reason I have a phi here and a L here is just to keep things general, so we're not actually jumping to the problem yet. This is just the general flow. So then to be able to plug in things we know, we need to do some algebra. So looking at our free body diagram, we can set up some equations for this to solve for what F actually is. And we know it's essentially a statics problem because Thraki's in equilibrium the whole time. So in the x direction, with to the right being positive, when we add up our forces, we get F plus, and then negative t sine theta. And just like I said, this should be equal to 0. And then in the y direction, we should get t cosine theta, because that's up and that's positive, plus negative w. And that will give us 0. So the way I like solving these is getting rid of the negatives by bringing the negative signs over, and then just dividing the equations. So we get there pretty quickly without having to do anything too bad. So then solving this however you feel comfortable doing, you should get F equals W tan theta. Anyway, we know what F is now. The only thing we need to figure out are what's P1 and P2, and what's cosine phi dl. So the way we can figure out what phi is note that in this equation, phi is the angle between dl and f. Well, if you look back at the picture of Thraki on the swing, that is f. So this angle right here between dl and f is theta. So phi is actually just theta. And then to figure out what dl is going to be, we know we can relate this s, this arc length, to r theta by the equation s equals r theta. So some small change along the arc would be dl. And that'll correspond with r times some small change along theta. So we end up getting that dl equals r d theta. And finally, this lets us know what we're going to be integrating with respect to, which is theta. That's our variable. So then to figure out where we're starting and where we're ending should be pretty simple. We know we're just going to start when Rocky's at the bottom. We're going to end at what they said was theta naught. So we start at 0, go to theta naught. And then after simplifying the tangent and cosine, we end up with the integral from 0 to theta naught of WR sine theta d theta. Then we can factor out a WR because they're constant in this integral. And then we just have the integral of sine theta, which is negative cosine theta. And we evaluate that from 0 to theta naught. And then we're left with negative WR times the quantity of cosine theta naught minus 1. And since we know cosine theta naught is going to be less than 1, it might be nice to pull this negative out, or we could just distribute this negative in, and we end up with the work done by the applied force, the person pushing on him, is W times R times the quantity 1 minus cosine theta naught. And this is positive. So for the evaluation, what we can do is, just to make sure we did this correctly, is that if we calculated the work due to the weight of Rocky, we should get the same answer, but negative. And the way we can check this, just to be interesting, is to use the vector form of the work integral. So what we'll do is we'll start with the general form. So work is equal to the integral from point 1 to point 2 of some force dot some length. So in this case, we know the force we're using is the weight of Rocky. So when we look at what these vectors actually are, the weight vector is actually just negative w, where w is the mass of Rocky times g, times j hat. J hat corresponds with the vector in the positive y direction. And then this negative sign lets us know that it's actually downward. And then dl is the interesting vector. We actually have two components of it. And if you look right here, all I did was zoom into this area right here. You can see that that makes sense. We can take this arrow and break it up into two pieces. You know that's theta. So dl times cosine theta gives you this. And then dl times sine theta will give you this. And the reason I use ds here is just out of convenience. And that's because in the original picture, we have that he covers an arc S. But you could have had this be dl and dl. All this is letting you know is that this ds is the magnitude of the dl vector. And then if we dot these two vectors, we should note that the weight vector did not have an I component. And the way you compute a dot product is you multiply like components. So we will do 0 times ds cosine theta plus negative w times d sine theta. So these two cancel out, and we're left with negative w d sine theta. So what that lets you know is that the weight doesn't do any work in the horizontal direction. It only does it in the vertical direction. And then when we simplify, we get negative w sine theta ds. So this is what we're going to integrate. And then plugging that into our integral, right, which is just replacing this stuff, we end up with the work is equal to the integral from 0 to theta naught, it would be the same bounds as before, of negative w sine theta r d theta. And just remember that the r d theta came from that dl equals r d theta. And since we're using ds, it's ds equals r d theta. And as you can already see, this is the same integral that we have right here. It just has a negative sign. So when you continue through, we'll end up with negative WR 1 minus cosine theta naught, which is indeed the opposite of what we got in part C. Now that was a little cumbersome, but it is good to see work calculated this way, because you will have to do it occasionally. But we could have done things more easily and noted that the work done by the weight of Fraki was just mgh, where h is the height that he traveled vertically. And if you look up here, the distance we have there is r times 1 minus cosine theta naught. That's the same as r minus r cosine theta naught cosine theta naught is this bit right there, and then r is this whole piece. So we end up just getting this to here. So we could have just used that, but it is useful to see this stuff worked all the way out.
Okay, so I hope that's a very long explanation on the problem. So I hope it is well defined. I won't go again with the example. So if you don't understand, so let's look back just the example and you can ask me a question later. Right? So let's continue. Okay, so the last one is in this chapter is the power. All right. So the power is the rate at which work is done. All right. And then the average power, all right, is PAV equals to delta W over delta T. Okay. And then the instantaneous power, all right. So is the instantaneous power is we have that as P equals to limit, okay, delta T goes to 0, okay, and then delta W over delta T, okay, where the dW over dt. Okay, so the SI unit of power is called the watt. Okay, let's say we have a box and we lift that slowly. So, okay, you do the work on the box to lift in the delta T within 5 seconds. So we have the delta W equals to 100 joule. Okay, so the average power is the delta W over delta T, which is 100 over 5, which is 20 watt. Okay, if we lift the box quickly, so before that we lift the box slowly. Okay, now we lift the box quickly. All right, so we lift to the same distance, but now with shorter time. Okay, for that we have 2 seconds. Now we have 1 second. So the power will be higher, right? So because we lift, okay, now let's say we lift this phone, okay, 2 seconds. Okay, now we lift quicker, right? It's less than 1 second. Of course, the power will be higher. All right, so in the mechanics, we can also express power in terms of force and velocity. All right, so the power is equals to F dot V, right? F dot V. So F is the force that acts on the particle and V is the velocity of the particle. Okay, so we obtain P as the instantaneous power. All right, so that's it for today. Any question? So we already finished up to chapter 6. All right, if there's no question, let's take. Any question?
The
Okay, so
tutorial,
pardon kalian?
the answer for tutorial, the one I
Okay.
asked.
All right, I will check after this. All right, after the class time.
Okay, okay.
Okay. All right. Okay, let's turn on your camera. Take your attendance today. All right, come on, everyone. Okay. So let me count from 10. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Cheers. All right. You can do any style that you want. Okay. One more shot. Okay. Thank you, everyone. So have a good day. All right. So bye-bye. Assalamualaikum.
Thank you, Doctor.
Waalaikumsalam. Thank you,
You're
Dokter.
welcome.
Thank you, Doctor.
Thank you, Doctor.